But I think that one picture emphasized to you how sensitive to climate change these animals must be. There's a wonderful spin-off from physics, from biology to physics in this, because the tags have temperature recorders on them, and when the narwhal is hungry, dives to 1,800 meters depth, if you can imagine. That's 180 atmospheres of pressure. They take data for physical science, and this is an element of serendipity, whale-based temperature profiling in Baffin Bay. And that's a long story and a beautiful one in itself. Well, so that's an example in which Kristen has worked and networked with Greenland in many significant ways, and there's been wonderful flow of ideas and technologies and results back and forth. The other example for today is our work with the Faroese Fisheries Laboratory, and Boje Hansen gave a wonderful talk about the global and local climate aspects of these islands, and Chalmar Hatun took that forward to biology and the ecology of fishing. Inseparable from this really is the Björknes Climate Center in Bergen, which is I think 90 scientists roughly in a great umbrella cast, sitting in the rain of the rainy weather of Bergen, the great umbrella agency which brings together so many climate scientists there, and their interactions with Faroes and with us is very, very strong. We are sister universities in sister cities. Well, the global story of climate research, it having this global exoskeleton, or I guess you'd say, involves recent news which is very compelling, and the technology involved is absolutely stunning. The Tau array is 70 moorings along the Pacific equator, put out by our faculty in the NOAA laboratory in Seattle, and it spans a quarter of the Earth's circumference from one side of the Pacific to the other. And this is documented El Nino, which is one of the globally important but tropically originating climate signals. Complementing that now is the Argo program of 3,000 profiling floats across the world's oceans. Only in this last year has this been achieved, but these dots here show the floats on the 4th of April 2008, almost fully populating the world ocean. And complementing these finally are the amazing technology of satellites scanning the Earth for currents, heat content, and temperatures and weather, and biological variables as you can see them at the surface. The internet itself is the central nervous system for all of this, and we couldn't be doing much of our work without the internet, and you know who invented that, right? So together these elements suddenly have produced a global real-time observing system for oceans and climate, completed only in 2007 for the first time. And yet they do lack one crucial element, and that's dealing with complexity. The Faroes Ocean region is both the focus of global climate, the headwaters of the great overturning circulation that Boje spoke about, and also a site of immense detail, which is completely necessary to understand either the physics or the biology of the region. And this is the fabric of sea surface temperature in false color shown earlier with Iceland and the Faroes, and these warm fingers of sea surface temperature reaching northward and helping to keep you warm and helping to determine ecosystem distributions. And so this is the global signal of a satellite altimeter, and that little circle there yet is so full of extra detail that we can't just sit and look from a satellite. We have to come here, and we have to join you in your interests in this region very closely. So the detail is not just at the ocean surface where satellites can see it, but ocean climate is a three-dimensional activity with veins and arteries that wind through the deep. I guess veins go one way and arteries go the other. This is the deep water going through the Faroe Bank Channel, Faroe-Shetland Channel, across the Iceland-Faroe Ridge next to Iceland, and then there's another branch off the picture in the Denmark Strait. And the red arrows on top are the warm Atlantic water exchanging for it, going northward into the Arctic, and eventually about to become deep, dense water. So our program here, using sea gliders, has been designed to resolve the kind of detail that you see in those figures. And they require, it's an inventive new technology. This is Charlie Erickson of our university who invented and has developed the Sea Glider. And it requires political skill, and there's a skillful politician. The Sea Glider is a particular technology that's led us to a 5-year journey through the ocean climate of the subarctic. It's an autonomous undersea vehicle. It does the work of a 30,000 euro per day ship at a small fraction of that cost. It's moved slowly, about 1/2 knot, about 25 centimeters per second, measuring key climate variables through the top 1,000 meters of the ocean: temperature, salinity, oxygen, biological activity. And they look a little like narwhal. These are narwhal here, and these are sea gliders. I'm not sure if they've ever met. They've actually been in the very same parts of the ocean in the Davis Strait together. And some of the further detail is on the screen. I won't go through that in great detail, but the main thing is that they are a real-time device phoning home like ET 3 times daily through this Iridium satellite network. Rather like a Mars probe, it can be controlled, and its engineering software can be rebuilt through the satellite link. So we are essentially driving these flying vehicles through the ocean. Powered by lithium batteries, their total power drain is 1/2 watt. And that means that on a set of batteries, you can nearly cross the Pacific Ocean on a liter of gasoline or petrol. A very efficient device. I don't think we could use it for personal transport.